Number 3 looks at the relationship between the equilibrium constant for the forward reaction and the reverse reaction, and also its relationship with Kp. So if we look at the balanced equation, ammonia is converted to nitrogen and hydrogen gas. The Kc for the reaction is given to us at 6.30 at 720 Kelvin. What is the Kc for the reverse reaction? So that's just something we hopefully learned in the chapter, that if we take the reverse reaction, the only thing we have to do for Kc of that reverse reaction, and we'll just say K reverse here just to give it a little bit of difference in Kc, we can say it's equal to 1 over the original equilibrium constant. Okay, it's the inverse. And so we say that's 1 over 6.30 here. And if we punch that in the calculator, we're going to get 0.159 as the equilibrium constant of the reverse reaction. Okay, so nothing bad there. But calculating Kp is a little bit more interesting. And we have to know our equation that Kp is going to be related to Kc, the equilibrium constant, but it's going to be multiplied by the ideal gas constant, and we're going to use the 0.082, we'll carry it on out, 0.6 liter atmospheres per mole Kelvin for the units for our gas constant, times the Kelvin temperature, raised to the delta N. So what's this delta N? For this reaction, delta N is the final number of moles in the product side minus, in the balanced equation, minus the reactant moles of gas. Okay, so it's the change in pressure is resulting here with a change in number of moles between these two. Now it's in equilibrium, so all three of these are present, but pressure is going to affect the equilibrium, and so we end up looking here, this is 4, 3 plus 1, coefficients of the balanced equation is 4 versus 2 moles on the reactant side. So overall, that delta N is going to be 4 minus 2 is equal to 2. Okay, and so if we say, all right, well, what's this going to work out to? 6.3 was the forward reaction. Calculate Kp for the reaction. 6.30 times the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin times 720 Kelvin raised to the 4 minus 2 or raised to the 2. Okay, so we end up getting 6.30 times, when we punch all that in, 57.787 squared, and then when we multiply it all out, we get 2.10 times 10 to the 4 for Kp. Now if you did use the reverse reaction, and so you replaced 6.30 with 0.159, the question wasn't exactly super clear on that, you would have gotten 4.76. So if you'd use Kc of the reverse reaction, we'd have seen 4.76 times 10 to the minus 5 for our Kp, our inverse Kp there. All right, so either one of those, considering the way it was worded, could have been what you'd go for, but the key is recognizing that change in moles and knowing that we're going to be using the 0.08206 gas constant when we are using this equation. Okay, final couple questions here. Will decreasing the pressure in the reaction shift the equilibrium right or left? Okay, so if we decrease pressure, decreasing pressure stresses the system to attempt to replace the missing pressure. Okay, so I got that all jumbled there. Let me move that out of the way. Okay, so what the system's going to want to do is it's going to want to increase the pressure when we decrease it. It's going to try to add more moles of gas. And so what ends up happening is if we decrease the pressure, the side that helps increase pressure is the right. It forms more moles of gas, so we're going to actually shift the equilibrium to the right, toward the product side, if we decrease the pressure. Increasing the pressure would do the opposite. It would shift us back left. An increase in temperature is observed as the reaction proceeds. Will adding heat to this reaction shift the equilibrium right or left? So if we're exothermic, that would mean that heat is a product and is released as equilibrium is established. Heat is released, and so that makes it a product. If you add too much of a product, it's going to shift the equilibrium back left to return us to Kc. It's going to get us back to the left, as we would see there, as if the heat is a product of the reaction. We'd see a shift back left.